We're going to talk today about quantum numbers and quantum theory. This leads into or leads from our discussion on the electrons in our previous video, where we were talking about photons and wavelengths of light and that sort of thing. So each atom has a specific spectra that we can look at, and we normally give you an opportunity to look through spectroscopes and be able to see these lines, but of course this year is a little different, so we're not able to do that. But we can look and we can see that each element has its own unique kind of fingerprint that allows us to identify what element it is. And this is how, by looking at these types of emission spectra, this is how they're able to tell like what types of elements make up different stars that are way off in the distance and that we would never have an opportunity to travel to, but they can go, oh, that star has hydrogen and helium and this and that. And so they're able to look at these spectra and break that down and be able to see it. Originally, it was proposed that hydrogen only had one allowable energy state. And now we know that there's different ones that it's able to go to. And you can kind of think of it as like kind of a ladder in a way, where there's different rungs of the ladder. And so if we're down at our base here, we're not going to give off any light. We're not going to give off any energy. But if we climb our ladder, and imagine that this is a vertical instead of a horizontal, if this was our ladder, we could climb up to the first rung. And if we jump down, we give off a certain amount of energy. And that energy is seen as red light. If we climb up to a higher rung, then we fall back down. We're going to give off more energy. And so we're able to see that and be able to see what type of lines are coming off. This is the visible light. There are infrared rays that are given off and also UV rays for hydrogen as well. So we talk about the ground state. And again, if you think of this in terms of a ladder, this would be the ground, the bottom floor, essentially. We haven't gained any energy. And this is where electrons like to stay. Sometimes, though, they do become excited because it's gained energy, but it's not stable in that format. And so the electron can't stay up there. It ends up falling back down. In the process of falling down, it gives off the energy in the form of light. There are different electron levels that are available, and electrons are only allowed in those certain levels. So just like a ladder, you're only allowed like to step on a rung. You can't put your foot in between the rungs and be able to stay there. These electrons aren't able to do that either. Smaller orbits, you're going to end up with energy levels that are closer to the nucleus, and they're going to give off less energy when they fall back down. Each element, though, each atom has only specific areas that these rungs are in. And so each ladder or each atom, each element has a different structure. And so each of their ladders, so to speak, look different from one atom or from one element to another. And so that's how they're able to distinguish from one element to another, is by looking at the light that's being given off. And we can determine what the last location of the electron is, and we're going to give that a value that's called a quantum number, and we'll also be able to give an electron configuration in our next section of this chapter as well. So these orbitals, they're not defined exactly, but we know with about 90% likelihood of where these electrons are, and the electron spends about 90% of its time in these boundaries. And these quantum numbers and also the electron configurations can be used to locate an individual electron, and so we'll be looking at that as well. So quantum numbers are acting like an address. They help us to locate an individual electron, specifically the last electron for a particular atom. So it takes a broad area and it's going to narrow it down to a very individual element on our periodic table. So it's kind of like taking the United States, taking that down to the state of Wisconsin, going to the city of Janesville, and then getting specifically down to a particular area, say Craig High School. So our quantum numbers will be able to do that. We're going to first start out with a periodic table that looks like this. You should have received one of these in class. Otherwise, you can go on Edmodo and download one. The first thing that we're going to do is we're going to identify different sections on our periodic table. The first section that we're going to do is the first two columns, and that is what we're going to identify as an S block. So pause the video, color those first two columns, and then down at the bottom, denote that that is the S block. Then you're going to go through and you're going to do the P block. That's over here. Do not color in this section. That should have actually been helium, which is located now over here. Helium then is not in the P block. It's actually in the S. I just drew it wrong here, but that's why the big X is there. And the P block, you're going to color in another color. That is going to be here. The P block then you will denote with colored pencil. Put that at the bottom. So pause the video and go ahead and do that. Next, you're going to draw in the S block, or sorry, the D block. The D block is here. That is the middle section of a periodic table. We call those transition metals. So color that, pause the video, color that in one color, and then denote that at the bottom. The next one is the F block. So that's going to be this section down here. Color that in a color, and then label that as the F, as in Frank block. The first part of the quantum number is denoted as N, and that's going to tell us how far away we are from the nucleus. That is kind of like in a building. It would tell us how far away we are from the ground floor. So the first level is the N equals 1, and then 2, and so forth. So we're going to draw that in our periodic table in a second. Here's the idea. The first level will have one sublevel. The second level is going to have 4 sublevels. So essentially you take this number and you square it. So for the N block, we would have 2 squared is 4. For if the N is 3, 3 squared is 9. And so forth and so on. So you can see as we get down here that that final level is 49 sublevels. That's a lot. So for our periodic table, we're going to put an N up at the top here, and then we're going to go through and we're going to label each one of these rows. 1, 2, 3, 4, 5, 6, 7. And since this section actually comes out down here, this is actually 6 and this is 7. So for the S block elements, whatever period they're in is our first number. So that's going to tell us if we're in this row, our first number for our quantum number would be a 1. If we're in this number, quantum number would be a 2, and so forth and so on. It's the same thing for the P block. So if we're here, the first number for our quantum number would be a 2. For the D block, though, it gets a little trickier. So for the D block, it's period minus 1. So if we're in this section, the first number would actually be a 3 because 4 minus 1 is 3. For the F block down here, it's going to be period minus 2. So anything in this row would be a 4 because 6 minus 2 is 4. And anything in this row would be a 5 because 7 minus 2 is 5. The next part is getting it narrowed down even further, and that's going to indicate which type of orbital we have. It indicates the shape, and we've already color-coded our periodic table to make this easy. So we have 4 different options, the S, the P, the D, and the F, and it's just giving us that shape. If we have an S orbital, it's a sphere, so that's easy to remember, S sphere. It's shaped like that. If we have a P block orbital, then that's going to be a peanut shape. So that's how we remember P, peanut. A D is a cloverleaf shape, and then the F is really complex. So here's a chart for that, and if we want to assign it a number, S is going to be a 0, P is going to be a 1, D will be a 2, and F will be a 3. So if we put that on our periodic table to make it easier, our L, which is our next number in this, is if we're in this S section, is going to be a 0, P will be a 1, a D will be a 2, and lastly our F will be a 3. And it just tells us the shape of the orbital that we're in. Next, it's going to tell us the spatial orientation. So kind of in algebra class, you had the X and the Y and the Z axis. This is just telling us how it is kind of oriented in space. And here are our options. If we're in an S orbital, it has to be a 0 because it's a sphere. So there is no three-dimensional option there. The P, however, is a -1, a 0, a +1. There's 3 different options. D, you can see those, and F, you can see those. So here's how we're going to assign that to our periodic table. Anywhere for an S, it's going to be a 0, so we just put a 0 down there. For the P, though, it's a -1, 0, 1, -1, 0, 1. D, we're going to do a -2, -1, 0, 1, 2, and then we repeat those over again. And then in F, we have a -3, -2, -1, 0, 1, 2, 3, and then again, we repeat. The last part of our quantum number is the spin, and this is going to tell us if the electron is spinning clockwise or if it's spinning counterclockwise, and we use a plus or a minus to denote that. And we'll talk about the concept of electrons filling energy orbital levels and that sort of thing when we get into electron configurations in the next couple weeks. So for this first column, it would be a plus. For the second column, it would be a minus. For the P's, we go plus, 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 and minus, minus, minus. For the D's, we do 5 pluses in a row, and then 5 minuses in a row. And lastly, for the F's, we do 7 pluses in a row and 7 minuses in a row. In the next video, I'll tell you how to determine the quantum number for specific